Explanation number 1. Syntax and semantics of if-else statements in common languages, see C++, Java, Python. General idea. An if-else selects one of two or more blocks of code depending on a condition that evaluates to true or false. Think of a traffic light. If the light is green, go straight, else red, stop. C or C++. If condition open brace statements executed when condition is true close brace, else open brace statements executed when condition is false close brace. The condition must be an expression of type bool or convertible to bool. Non-zero integer values are considered true. Braces are optional for a single statement, but using them improves readability and avoids the dangling else problem. Java, if condition open brace true branch close brace, else open brace false branch close brace. Java requires the condition to be a Boolean true or false. No implicit conversion from integer to Boolean is allowed, which makes accidental bugs rarer. Python, if condition true branch else false branch. Python uses indentation instead of braces. The colon marks the start of the suite. Any expression that evaluates to a truthy value, such as non-zero or non-empty, counts as true. The condition is evaluated once. If it is true, the true branch runs, otherwise the false branch runs. Only one of the two branches is executed. There is no fallback after the first branch finishes unless the programmer nests another if inside. In all three languages, the scope of variables declared inside a block is limited to that block in C, C++, Java, or to the indented suite in Python. A Boolean expression combines one or more atomic conditions using logical operators. The result is either true 1 or false 0. Ampersand and true only if both operands are true. Pipe or true if any operand is true. Exclamation mark not flips true to false. In Python, the words and or not are used. In Java, they are the same as C, ampersand, pipe, exclamation mark. Truth tables A and B, A or B. Row 1, false, 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 false. Row 2, false, true. Row 3, true, false, false, true. Row 4, true, 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 true. Example, determine if a year is a leap year. Bool is leap equals year modulo 4 equals 0, and year modulo 100 not equals 0, or year modulo 400 equals 0. Break it down. Year modulo 4 equals 0 is A. Year modulo 100 not equals 0 is B. Year modulo 400 equals 0 is C. The overall expression is A and B or C. Using a truth table, you can verify that the expression is true only for years that satisfy the Gregorian leap year rule. Short circuit evaluation. In C, Java, Python, and stops evaluating as soon as the result is known. Example. If x not equals 0 and y divided by x greater than 2 avoids division by 0 because x not equals 0 is checked first. This property is useful for protecting against runtime errors and for writing compact guards. Compound comparisons, Python only. Python allows a less than b less than c, which is equivalent to a less than b and b less than c. It saves parentheses and makes the code read like a math statement. Understanding the truth table helps you predict the outcome of any combination, avoid logic bugs, and design clear conditions. Explanation 3. Structure, flow, and readability of nested if statements including depth considerations. What is a nested if? An if placed inside the true branch or false branch of another if. It resembles a decision tree. Each node asks a question, each edge leads to another question or a leaf answer. Visual analogy. Imagine a series of checkpoints in a museum security line. Person A is checked for a badge. If they have it, they go to a second checkpoint, for example, metal detector. Otherwise, they are sent to a different line. Each checkpoint is an if inside the previous one. Typical structure, C style. If cond 1 open block level 1 true, if cond 2 open block level 2 true, if cond 3 open block level 3 true, deepest leaf close block else open block level 3 false close block else open block level 2 false close block else open block level 1 false alternative branch close block. Readability tips. Limit depth deeper than 3 to 4 levels becomes hard to follow. Consider breaking the logic into separate functions or using early returns. Consistent indentation. Most IDEs automatically indent. This visual cue mirrors the logical hierarchy. Descriptive condition names instead of raw expressions, store them in well-named booleans. Bool has passport equals. Guard clauses early exit invert the nesting. If not cond 1 return fail fast. If not cond 2 return. Now we are guaranteed that cond 1 and cond 2 are true. Depth considerations. Time cost. Each level adds a constant time check, so total time is O of depth, usually negligible but deep nesting, combined with large loops can impact performance. Maintainability. Each additional level multiplies the number of distinct paths 2 to the depth for binary decisions. Documentation and unit tests become essential. Stack usage. In most languages, the if statements do not create a new stack frame. Only function calls do so. Nesting itself does not risk stack overflow. When to avoid nesting. When the same condition is used in many places, extract it. When you can use a switch multi-way selection or a lookup table array dictionary instead. When the logic can be expressed more declaratively using standard map of handlers. Overall, treat nested ifs as a tree diagram on paper first, then translate to code with clear indentation and early returns to keep the tree shallow. 4. Common pitfalls: dangling else, if ladders, and logical errors in compound conditions. Definition: when an else could be paired with more than one preceding if. The language chooses the nearest unmatched if. Why it matters: the intended pairing may be different from what the compiler decides, causing subtle bugs. If A then if B, then do something, else do other. The else attaches to the inner if B, not the outer if A. If A open brace, if B open brace, do something, close brace, else open brace, do other, close brace, close brace. Python does not suffer from this, because indentation makes the pairing explicit. 4.2 Else if ladders, also called if-else chains. If condition 1, open brace, close brace, else if condition 2, open brace, close brace, else if condition 3, open brace, close brace, else open brace, close brace. First pitfall: order matters, the first true condition wins. Placing a broad condition early can shadow later more specific cases. Second pitfall: repeated work. Each condition may recompute the same sub-expression, hurting performance. Third pitfall: readability. Long ladders greater than 5 become unwieldy. Good practice: arrange from most specific to most general, and factor common sub-expressions into variables. 4.3 Logical errors in compound conditions. Missing parentheses, operator precedence can flip the meaning. For example, intended open parenthesis x greater than 0 and y greater than 0 close parenthesis or z equals 0. Written as if x greater than 0 and y greater than 0 or z equals 0, which actually evaluates as open parenthesis x greater than 0 and y greater than 0 close parenthesis or z equals 0 close parenthesis. Adding parentheses clarifies the intent. Using assignment equals instead of equality equals, a classic C bug. If value equals 5 in the condition, it assigns 5 then tests true, so the condition is always true. De Morgan's law mistakes when negating a compound condition. Correct negation of A and B is not open parenthesis A and B close parenthesis, which is equivalent to not A or not B. A common wrong version is not A and not B, which actually negates A or B, not A and B. Floating point comparison, direct equality on doubles is unsafe due to rounding errors. Safer to check if the absolute value of a minus b is less than 1 times 10 to the minus 9. 4.4 Checklist to avoid pitfalls. 1. Always use braces in C and Java even for single statements. 2. Indent consistently, most editors can auto-format. 3. Add parentheses around compound conditions for readability. 4. Write unit tests for each branch of an if-else ladder. 5. Enable compiler warnings -wall in GCC. They often catch assignments in conditionals. By being systematic, you can eliminate the most common logical bugs that arise from if-else structures. A decision tree is a flow chart-like representation where each node asks a yes or no question or multi-way question, and each edge leads to another node or a leaf answer. Implementing such a tree with if-else statements is straightforward because each node maps to a conditional block. The step-by-step design process. Step 1. Define the problem. What do you need to decide? Example: classify a triangle given 3 side lengths. Step 2. Identify the decision points. List the predicates that split the input space. Step 3. Order the predicates. Place the most discriminating those that prune the search space the most near the top. Step 4. Draw the tree sketch boxes and arrows. Each leaf contains the final result. Step 5. Translate to code. Each box becomes an if or else, if, and each leaf becomes a return or assignment. Step 6. Test every path. Ensure each leaf can be reached with some input. Example triangle classification C++. A num triangle, not a triangle, equilateral isosceles scaling function classify takes a BC of type double, returns triangle. If a plus b less than or equal to c, or a plus c less than or equal to b, or b plus c less than or equal to a, then return not a triangle. If a equals b and b equals c, then return equilateral. If a equals b or a equals c or b equals c, then return isosceles, return scaling. The tree has 4 levels: validity, equilateral, isosceles, scaling. Each return acts as a leaf terminating the function early. Example loan approval decision Python. Function approve loan takes credit score, income, existing debt, loan amount if credit score greater than or equal to 750, then return true if credit score greater than or equal to 650. Then compute DTI as existing debt divided by income. If DTI less than 0.4, then return true, else return false, return false. Here a nested if is used to evaluate a secondary condition only when the first condition is met. Tips for robust decision tree coding. Use early returns rather than deep nesting. When possible, it keeps the tree flat and each path obvious. Encapsulate predicates in well-named functions. Boolean is eligible integer age, returns age greater than or equal to 18, if is eligible age then. Validate inputs at the top of the function, treat them as the root guard. Avoid duplicated logic. If 2 leaves share a common sub-condition, factor it out. By following the tree design methodology, you transform a complex decision problem into a clear cascade of if-else statements that is easy to read, test, and maintain. 6. Time complexity analysis of nested conditional structures. The runtime of an if-else cascade is dominated by the number of conditions that are evaluated for a given input. Unlike loops, there is no iteration, so the cost is O1 in the worst case if the number of conditions is bounded by a constant. Simple linear chain. If C1 then ellipsis else, if C2 then ellipsis else, if C3 then ellipsis else ellipsis. In the worst case, none of the first 3 conditions, true 3 predicates, are evaluated O of k, where k equals number of branches. Since k is usually a small constant, we treat it as O1. Deeply nested tree. If C1 then, if C2 then, if C3 then leaf. The worst case path length equals the depth d of the tree. Runtime equals O of d. If the tree is built from input data, for example, a decision tree stored in a structure that can grow with n inputs, then d can be O of log n for a balanced tree or O of n for a degenerate linked list-like tree. Example binary decision tree for searching a value. A balanced binary tree with n nodes has depth approximately log base 2n. Bool search node star root comma int key open brace. If not root, return false. If key equals root arrow value, return true. If key less than root arrow value, return search root dot left comma key, else return search root dot right comma key close brace. Each recursive call adds 1 if evaluation total calls equal depth O of log n. Influence of short circuit evaluation. In compound conditions, A and B and C evaluation stops as soon as one operand is false. Best case cost may be O1 first operand false, worst case cost O of m, where m equals number of operands. Practical guidelines. Count the longest path through the conditional logic that gives the worst case complexity. If the path length depends on input size, express it using n, for example log n or n. Use early exits to keep the average path short, especially when many inputs fail early checks. When the decision process is large, consider converting the cascade into a lookup table or hash map average O1 lookup. In most classroom problems, the depth is constant, so we report O1. For algorithmic problems that build a decision tree from data, use the appropriate logarithmic or linear bound. 7-point equivalence and conversion between if-else, switch case, and ternary operators. 7.1 If-else versus switch. When to use switch, the condition is a single variable or expression, evaluated against constant integral or enum values. When if-else is better, you need range checks complex Boolean expressions or non-integral types. If day equals 1, then print mon, else if day equals 2, then print 2, else if day equals 3, then print wed, else print other. Switch day case 1 print mon break case 2 print 2 break case 3 print wed break default print other. Both produce the same flow, but switch can be more compact, and in some compilers generate a jump table for O1 dispatch. 7.2 If-else versus ternary. The ternary operator is a compact expression that returns a value. Syntax condition expression if true expression if false. Only suitable when you need a single value, result not multiple statements. Int max equals a greater than b question, mark a b replaces, if a greater than b max equals a else max equals b. The ternary is an expression. It can appear inside larger statement system out print line score greater than or equal to 60 pass fail. Limitations nesting ternaries makes code hard to read, and you cannot place statements like print directly without wrapping them in a function call. 7.3 Converting a complex if-else ladder to switch. If conditions involve ranges, you can map them to discrete cases using arithmetic. Classify month into season. Northern Hemisphere int season equals month divided by 3 0 to 3 switch season case 0 print winter break case 1 print spring break case 2 print summer break case 3 print fall break. Here the if-else version would compare month ranges. The arithmetic conversion yields a clean switch. 7.4 Summary table. Construct if-else typical use. Arbitrary Boolean expressions can handle ranges yes via and or returns a value no needs assignment. Typical performance linear in number of branches often O1. Construct switch typical use. Single integral or enum expression can handle ranges no needs discrete constants, returns a value no. Typical performance often O1 via jump table. Construct ternary simple two-way choice can handle ranges no, returns a value yes. Expression typical performance same as single if constant time. Performance differences are usually negligible. Choose the style that makes the code most readable. 7.5 Practical advice. Readability first. If a switch makes the intent clearer, use it. Avoid dangling else braces for if-else explicit break in switch. Prefer ternary for simple assignments, never chain more than one level deep. When converting, test each path. Small logic mistakes, such as missing break produce fall through bugs. By understanding the equivalence, you can pick the construct that best matches the problem's nature and keep the code clean. Question 1 Prime check in C++. Problem: write a function bool is prime of int n that returns true if n is a prime number greater than 1, divisible only by 1 and itself. Use if-else statements only, no loops are allowed. Solution uses early returns and a few if statements. The loopless requirement forces a simple deterministic test for small n. If n less than 2, return false. If n equals 2 or 3, return true. If n modulo 2 equals 0, return false. If n modulo 3 equals 0, return false, return true. The first if guards the trivial non-prime case. The second if handles the two smallest primes. The third and fourth if eliminate obvious composites. The final return true acts as the default else branch. Question 2 Triangle classification in Java. Problem: given 3 side lengths a BC double, output one of the strings not a triangle, equilateral, isosceles, or scalene. Use nested if-else statements. If a plus b less than or equal to c, or a plus c less than or equal to b, or b plus c less than or equal to a return not a triangle else. If a equals b and b equals c, return equilateral else. If a equals b or a equals c, or b equals c, return isosceles, else return scalene. Outer if is the guard that rejects impossible triangles. Inside the else block we have a nested ladder. First test for all 3 sides equal, then test for any 2 sides equal, finally if none of the above it must be scalene. Question 3 Grade calculation in Python. Problem: write a function grade of score that returns a letter grade according to 90 to 100A, 80 to 89B, 70 to 79C, 60 to 69D, less than 60F. Use a single if a if-else chain and the ternary operator for the final return. If 90 less than or equal to score less than or equal to 100, return A. Else if 80 less than or equal to score less than 90, return B. Else if 70 less than or equal to score less than 80, return C. Else if 60 less than or equal to score less than 70 return D. Else return F if score less than 60 else invalid. The chain checks the highest range first. Once a condition matches, the function returns immediately. The final else uses a ternary to distinguish a genuine failing grade F from an out-of-range input invalid. Remarks for exam takers: always draw the decision tree before coding. It prevents missing branches. Use early returns to keep the code flat and avoid deep nesting. Remember to handle edge cases such as exactly 90 negative scores, non-numeric input. Write short self-explanatory condition names if the language permits Boolean is valid equals. These three problems illustrate typical uses of if-else, guard clauses, nested classification, and ladder selection, and provide fully working solutions in three popular languages. 9. Debugging strategies for conditional logic errors: trace tables, breakpoints, and code walkthroughs. 9.1 Trace truth tables. What it is: a manual spreadsheet-like list that records the values of every variable and the result of each condition for a set of test inputs. How to use: Step 1. List all input variables as columns. Step 2. Add a column for each intermediate Boolean expression cond1, cond2, and so on. Step 3. Add a column for the branch taken, example a BC. Step 4. Fill rows with representative test cases, especially edge cases. Example: debugging a nested eligibility test. Row A: applicant at age 17, income 60,000, credit 720, age greater than or equal to 18. False: income greater than 50,000, true credit greater than 700, true branch else age fail. Row B: applicant B, age 22, income 45,000, credit 710, age greater than or equal to 18, true income greater than 50,000, false credit greater than 700, true branch else income fail. Row C: applicant C, age 30, income 80,000, credit 680, age greater than or equal to 18, true income greater than 50,000, true credit greater than 700, false branch else credit fail. Row D: applicant D, age 40, income 90,000, credit 750, age greater than or equal to 18, true income greater than 50,000, true credit greater than 700, true branch approve. 9.2 Breakpoints and step through debugging. Set a breakpoint on the line containing the if statement. Run in debug mode. The execution halts before the condition is evaluated. Inspect watches. Add the condition expression as a watch to see its Boolean result. Step over F10 to execute the true branch. Step into F11 to dive into a function called inside the branch. Tip for nested ifs: place breakpoints on each level. This helps you confirm that you entered the expected depth. 9.3 Code walkthrough rubber duck debugging. Explain the logic aloud or to a rubber duck. While narrating, you often spot missing parentheses or wrong operators. Write pseudocode first. A plain English description of each decision, then translate to code. Check for dangling else. Verify that every else is paired with the intended if. Adding braces C or Java or extra indentation Python resolves ambiguity. 9.4 Automated unit tests for each branch. Write a test case for every leaf of the decision tree. Use a testing framework: JUnit, PyTest, Google Test. Example: JUnit. Test annotation public void test. Approve high score open brace assert true lone dot. Approve open parentheses 750, 100,000, 0 close parentheses semicolon comment should hit high score branch close brace. Test annotation public void test. Reject low score open brace assert false lone dot. Approve open parentheses 600, 30,000, 10,000 close parentheses semicolon comment low score branch close brace. When a test fails, the framework tells you which assertion failed, narrowing down the problematic branch. 9.5 Common debugging checklist for conditionals. Item 1 Correct operator versus equals and versus ampersand. Item 2 Parentheses, are they grouping as intended? Item 3 Data type mismatches comparing int with float may cause rounding surprises. Item 4 Short circuit side effects, ensure any needed side effect is not hidden behind a later operand that never executes. Item 5 Off by 1 errors, especially with range checks less than or equal to versus less than. Item 6 Floating point tolerance, avoid direct equality. Item 7 Logical negation, applied to Morgan correctly. 9.6 Real-world analogy. Think of a security checkpoint with multiple guards. Guard 1 checks ID, Guard 2 checks baggage, Guard 3 checks metal detector. If any guard says no, you are stopped. To debug why a person was turned away, you interview each guard trace table and watch their decision breakpoint. You also write down the exact rules. Each guard follows unit tests to guarantee consistency.